Hi, and welcome to 8.1a, Work 1. We split this up into two sections. In this lesson, students will be able to describe and calculate the work done on an object. Students will be able to recognize when to break vectors into components in order to calculate work. So that vector component thing keeps popping up again and again. Students will be able to determine the work done by analyzing a force versus displacement graph. So graphs keep on coming up again and again as well. So here it is, work. We use a capital W in our equations to represent work, and the definition says work is done on an object when a force causes the displacement of an object. So you might have said to yourself, man, I did a lot of work last night writing that essay, and if you were typing on a keyboard, actually you didn't do that much work at all because the force required to move the key is not that much. And think about the displacement of the key. It's not that much. Now, you're pressing the key a lot of times, so I guess it might add up to some amount of work, but it's not as much work as you think it was. So now we're thinking about work in terms of the physics definition. Now, you might have seen this in a previous science class. We're talking about work, force times distance. It says work is done only when components of a force are parallel to that displacement. So again, in that example that I just gave, the displacement vector and the force vector are both parallel to each other. Now you could have some weird angle if you were typing from some weird angle, you could exert a force that way, but only the component of the force that acts parallel to the displacement is the thing that's doing work. You're just overexerting yourself if you exert another force this way that's not causing a displacement. You're not doing any work by that force. So we have force and displacement. Keep in mind that they have to be parallel. And then in the parentheses, it says work is a scalar quantity. So the direction actually doesn't matter when you're talking about like adding the work together. What is the total work done? It's a scalar quantity, so you wouldn't associate a direction with the amount of work. You associate direction with the things that make up the work, but it's just the amount of energy really that you're putting into the system or taking out. So here's our equation. Work is equal to the force times the displacement. And what do you think the units of work should be? You might say a Newton times a meter, and that's fine. You won't get points off if you write Newton meter. All right, so I did 5 Newton meters of work. But if you do a lot of work, there's a different unit for it. We won't use Newton meters. If you do a lot of work in your life, you can make a lot of money and you could buy a lot of joules. So the unit for work is joules, not joules like gems and jewelry, but joules like that. So, yep, you could write a Newton meter instead. That shows that you know what work is, force times displacement. And just as a point of reference, it takes about 1 joule of energy to lift an apple from your waist to above your head. And normally I would stand in front of the screen in the classroom and I'd put my hand over here and magically I would lift the apple about 1 meter above my head. So if you think about it, like if the apple weighs 1 Newton, I need to exert 1 Newton of force to lift it against gravity. And I'm exerting that force over a distance of 1 meter. So yeah, that would be about 1 joule of energy. Just as a reference for what 1 joule would be, or lifting an apple above your head. Okay. So where is the formula for work? It's going to be on the back page. So can you see it? Work is equal to the force times displacement. Now this is the introduction to Unit 8, which is work, power, and energy. And actually, the amount of work you do is equal to the change in the total energy of the system. So here it is, ET, the total energy. We're not going to talk about energy yet. First, we'll talk about work, and then we're going to talk about power, and then we're going to talk about kinetic energy, so work, power, energy, gravitational potential energy, elastic potential energy, which has to do with springs, and this formula is called Hooke's law, and that has to do with springs as well. So energy, work, power, and then we relate everything together with the conservation of energy at the end of the unit. And then we take a nice test, and it's a lot of fun. So example 1, very straightforward, says a 30 Newton force is used to push a 5 kilogram block a distance of 4 meters. What is the work done on the block? As promised, pretty simple to begin with. The force is 30 newtons. The distance, the displacement is 4 meters. And from this diagram, we can assume that the displacement is to the right. So the force and the displacement vectors are parallel to each other. We could use that as a little side note. You know, we could draw a free body diagram. This is Fg, this is the normal force. And I'll ask you, how much work is the weight doing? You're exerting a force. How much work is that force doing? Well, we're not being displaced downward or upward, so the weight is not doing any work. It's the applied force that's doing the work over the 4 meter distance. So not that I'm making it too complicated, but just take my time with this. The work is equal to, we don't know. So W is equal to FD. W is equal to 30 times the 4. So we have 120. And what are the units for work? So wake up now, because I know that was kind of straightforward. Do you remember? What are the units for work? Remember, if you do a lot of work, you could buy a lot of joules. Joules, capital J. All right, so that was a little bit too easy. Let's throw a graph in the mix. It says a child pushes their wagon at a constant speed along a level sidewalk. The graph below shows the force applied and the distance the wagon moves. So it looks like they're applying this 30 Newton force. It's always 30 Newtons. And the question is, what is the total work done by the child in pushing the wagon only 3 meters? So how much work is done after they go 3 meters? You might say to yourself, okay, since the force is constant, I know that F is always equal to 30, and the distance that we care about is equal to 3 meters, so I could definitely find the work. It's equal to 30 times 3, or 90 joules. But if you remember, when we were analyzing graphs in the kinematics unit, we kind of did this in a different way. We said that the force is on the y-axis, so that's like the length of a square, and the distance is like the width of a square. So you could actually find the area underneath the curve. In a F versus D graph, the area is equal to the work. So that area is equal to 90 joules of work. You might say to yourself, okay, but the formula works just fine. Why the heck would I need to know that? If the force varies, you could see on this graph, if you think about it, the force starts at 0 and then you slowly increase the force that you're applying. So you're pushing harder and harder and harder on the wagon, okay? Then you can't just do W equals FD, because what would you plug in for F? 0, 40, you know. Let's look at this graph. If we know that the area under this curve is equal to the work, then at 3 meters, we can draw ourselves a triangle and then just calculate the area of that triangle. So you do 1/2 base times height. The base of the triangle is 3 meters. The height of this triangle is 30 newtons. So you get 45 joules of work being done. Less than before because you're not pushing as hard on the block. You get there eventually, but not in the beginning. So yeah, this is actually a calculus thing called taking the integral. It's the area under the curve. That's as advanced as we'll get, but what happens if the curve is like a parabola? then you'd have to take the integral instead of just finding the area underneath this, because how would you find the area of like this shape? It's a weird looking shape. Okay. So, too easy still, you say. We've seen that before. Critical, I want to try to trick you now. It says critical thinking. A student does 300 joules of work pushing a cart 3 meters east. So there's 300 joules here. And then 400 joules pushing the cart 4 meters north. So they do 300 and then 400 joules of work. This person's doing a lot of work here. What is the total amount of work done by the student? Pause the video and think about it. I know you didn't pause it, so remember the definition of the work. Now, pause the video and think about it. Go back to your notes that I know that you wrote down when I did that slide. Pause the video. Oh, you didn't write down the notes? Maybe you should write them down now, because work is a scalar, people. Were you trying to do like a 3, 4, 5 triangle type of thing with this? Work is a scalar. You don't add the vectors just like this. Just because you see arrows doesn't mean you always have to do the vector thing. So yeah, this was 300, this was 400, but this isn't 500 joules. You didn't do 500 joules of work. You get credit for all this work you just did. You did 300 joules plus another 400 joules. You did 700 joules of work. Work is a scalar quantity. You just add them all together. The direction doesn't matter when you're finding the total work. Like this right here, I don't want to see that for the total work. There is a time and a place for adding vectors like that, but finding the total work done is not one of them. If you wanted to say, oh, my actual displacement was 5 meters, that's fine. But no, you did 300 joules and then you did 400 joules and you get credit for doing all that work. Okay, cool. Critical thinking, 2 out of 3. Have you ever watched Survivor before? This is a plug for Survivor. It's a fun show. It says Shoulder the Load is a recurring endurance challenge in Survivor where contestants try to hold up as many bags of water as possible. How much work are their survivors doing? So let's just say this stays completely still the entire time. These bags don't move because this person's going to win right here, okay? How much work are they doing? It's going to get really heavy. Remember, work is equal to the force times the displacement. And we just said there is 0 displacement. Oh, I should have told you to pause the video. Did you pause the video? I don't know. Did you think about it? If there's no displacement, then W equals FD, W equals F times 0. She's actually not doing any work, and neither is this guy. All right, it's only when the bags start moving down that they're like doing work against gravity. Tricky stuff, so no work being done because they're not moving. All right, so here's a kind of tricky one. It says an elephant carries a bucket with a weight of 20 newtons, a distance of 30 meters at a constant velocity. How much work is being done on the bucket? Pause the video and think about it. Well, the displacement of the bucket is this way, and the elephant is lifting upwards on the bucket this way. And we said that work is done only when components of a force are parallel to the displacement. And as you can see, these two vectors are not parallel to each other. All right, so actually no work is being done on the bucket. If it said that the elephant was lifting the bucket upward, obviously there would be some work. But you might say to yourself, well, he's moving it forward. Doesn't he get credit for pushing it forward? The inertia of the bucket is actually the thing that's keeping the bucket moving forward because it says it's at a constant velocity. If he was pushing a little bit harder, then there might be a little bit of a component pushing in that direction to cause you to accelerate. But since you're not accelerating and it's a constant velocity, then the forces are all balanced and it's just the inertia of the bucket that keeps it moving. To get it started moving, the elephant did some work. It had to accelerate it from rest, unless this elephant just always had the bucket in its trunk. So that's kind of interesting too. Remember that about the parallel components. Because we're going to talk about it right now. It says work is only done by the components of a force that are parallel to the displacement. So if you're pulling upward on a box like this, only part of your force is doing work. We know that W is equal to FD, but let's draw in the part of the force that is doing the work. If our displacement is to the right, we want the component of the force that's pointing to the right, Fx. And we know the shortcut by now. It's been a few months now. Fx is equal to F cosine theta, and we know it's cosine because this is adjacent to the angle, adjacent in hypotenuse in this triangle. All right, so let's plug that in instead. We have W is equal to the x component of the force times the displacement, which is equal to F times cosine theta. But normally people don't write it like this, right? F cosine theta d. That's not cool. We want FD cosine theta. So it's basically the formula times the cosine of the angle when the angle given agrees with the shortcut formula. So typically it will, like this example does. It says a child applies a constant 40 Newton force along the handle of a wagon, which makes a 30-degree angle with the horizontal. How much work does the child do in moving the wagon a horizontal distance of 10 meters? Pause the video. I know, come on, pause the video and try this one on your own. This one's like a good, decent challenge. All right, here we go. So we have an applied force of 40 newtons. If you use that in W equals FD, that's not going to be good. We know the angle is 30 degrees. We know the displacement is 10 meters. And we know that it's only a part of this force acting along. Just like we said, this is applied force. That's what they're actually pulling. But only a part of that force, Fx, the x component of that force, is doing work. The other part of the force, Fy, is that doing any work? No, because your displacement in the y direction is 0. There is no displacement in the y direction unless they say that they're lifting the thing up off the ground as well. But this component of the force is not doing any work. It's only the x component. So you could find the x component first if you wanted to. I show it here in two different ways. This is like the old school way, just the definition of cosine adjacent over hypotenuse. You plug in adjacent and the hypotenuse. This is the x component of the force that we'll use. Or if you want to use the shortcut formula, because again, it's just the force times the cosine of the angle. So that's where the shortcut comes from. This force is F, all right? Then you also get the same number. And then you plug it in your work formula. And you get 346. What are the units? If you do a lot of work, you get a lot of joules, okay? Remember, this is the x component of the force because we're talking about a displacement in the x direction. All right, don't forget that. Alternatively, you don't have to do like one step and then two step. You can do it with that formula we just introduced, where the work is equal to F d cosine theta. You're doing it all in one shot, and that means this F is your hypotenuse, all right? By doing times cosine theta, that's helping you find the component of the force there. So what does that mean? That means we'll plug in W is equal to 40 newtons times the displacement times the cosine of the angle. It's really, you're just multiplying the stuff together, right? All right, so you get the same thing. 346 joules of work done by that kid. Nice. Now it's time for you to do some work. That's about it. Thanks for watching and have a great day. Do some work.